Hi everyone, I am Siddhartha and I am joined by my friend Samir today. We are from VTU and we would like to present our research on HANDS, which is an anomaly detection system which uses neuromorphic computing. So, yeah, that's a lot of words. I don't know if how many of you could keep up. We also call that word salad, really. Let's unpack this one at a time. I would like to start with the anomaly detection part and I would like to give it to Samir to do that.
Uh, Hello, everybody. So we'll start with anomaly detection. So anomaly detection is when you have a stream of data or a source, anything. It is finding out stuff that does not belong. As in point. Next, moving on. Here we have a very standard signal of an ECG here. This could be any one of yours right now. But in here you can see there is one small error, right? We have a anomaly detected. That could be bad, that could be good. We do not know because it is probably detected too late. Here, okay, next one. Anomalies are everywhere. You could find it in your large data sets, in your LLMs, wherever it may be. It is finding the anomalies at the beginning of the where it is at your edge case, where it is probably the most efficient. Why do we care? So, detection, let's say you have a large scale system where you have a central computing power distribution system and edge processes, edge computing nodes, let's say edge computing nodes as well. Now, usually, if you have sensor data goes through the edge computing, through the middle management, whatever software you have, and then to the computing power, right? And usually, you'd find the error at the computing power, but that causes a lot of delay. That causes a lot of use case to solve that, especially. And anomaly detection at the endpoint feels like overkill a bit. If you have another anomaly detection pipeline, another system just set up just for that, it feels a bit overkill. And it is at the point, because resources on IoT devices, which is usually what you're using at the endpoints, are very, very limited. In actual use cases, it's not very system heavy, you would say. It's very limited. Here's why. Okay, if you can implement anomaly detection right at the edge case, it saves an enormous amount of time and compute power in the long run. Error correction algorithms can be tailor-made for the device, so whatever data you're getting, you can make we can make the algorithm directly for that, and it reduces the overall stress from the entire system. I'd like to talk about some traditional approaches to uh, anomaly detection. One is the statistical rules like z-score and median absolute deviation, or MAD. These are easy to understand and explainable, but they start breaking if your baseline shifts even a little. Another one is machine learning. Everybody knows this. You train some data and you get results. But some of them would be SVM for autoencoders, that kind of thing. But these can spot subtle patterns very, very well, but they require an immense amount of training and data, and they need a lot of careful tuning to actually work. And then there's predictive modeling. You forecast what normal behavior looks like and flag anything that deviates. But the problem with this is that this works well only if you have data that is very stable, and real life is rarely stable. But if the data shifts, the model performance can drop very quickly. Real life is very, very uncertain. So there's another learning process called neuromorphic computing that I would like Siddhartha to come and explain.
Yeah, thank you for that, Samir. So, yeah, as he said, real life is very uncertain, unstable, and there's no amount of training that you can give to a machine to actually, handle that sort of uncertainty. But we can try. And that's what neuromorphic computing is all about. It's about computing like your brain does. So, let's go ahead. So, yeah, what do we do here? Please go back. Yeah, we don't want big batch processing. That is what ML does. We want something that is event driven. You compute on the fly basically, and you don't have a lot of retraining. And every time your data shifts, you don't want to globally retrain. So let's go ahead. Yeah. So what are basically neurons? You've all heard of neural networks. It's pretty much the same here in neuromorphic computing. So here we say that the neuron gives a spike on an input which crosses a threshold, which is very similar to the activation function in neural networks. So the computation actually happens in the timing and in the pattern of these spikes which occur. And just like your brain has linkages between neurons in your head, they are called synapses. Here also we have synapses, but these synapses are systems that update their data locally, depending on what input is coming in your. You might have a rolling window or some sort of other estimator. So depending on what it sees, it will update itself locally. So yeah. So why are we talking about neuromorphic computing in the first place? Because in neuromorphic computing, there are some advantages you get without, instead of your ML. So the systems are sparse and they are very event driven, which means they consume very little energy. They only consume energy when such input is detected that crosses the threshold. And that's why it is important. And another thing is that computation is local and temporal. What does that mean? So, temporal is so these synapses aggregate their input over time, which means uh, without global training like ML, you can get the patterns. Say, for example, your data is shifting to a particular point, it's kind of drifting, right? You cannot really sense that without in ML, without having to do some training based on different parameters. Whereas when your neurons aggregate such inputs, you can easily sense the shift in the data. And local computation means the same thing. The parameters are not global. Whatever is input in the channel at the time, that is what is input to the neuron. Yeah. So again, to recap the advantages, we have energy efficiency. We want to run this on edge devices. So let's say ESPs or node MCUs or whatever. So energy is the resources are very limited on IoT devices. So adding these sort of neural networks could help be very energy efficient. One second, go back. One second. Yeah, temporal sensitivity as well. As I said, it's difficult to catch the patterns in traditional ML or other statistical based anomaly detectors, whereas we can easily detect them here because of the aggregation of the neurons. And interpretability, last one, we have, say, for example, sometimes when you use ML, it can feel very black boxed, like you don't know what's going on behind the layers of all those neural networks. But here, you can isolate each neuron and check the output. Like when I said the neuron spikes, right? So each spike carries a little bit of information which you can isolate and derive later. You can get that information later. So again, we've talked about the advantages, and nothing has advantages without limitations. So, what are the limitations in neuromorphic computing? First of all, it is a very developing field, and the ecosystem and the tools are all very developing. A lot of people would not have heard about it, and the support will be very less for neuromorphic computing. And a little, for complex tasks, building such networks and training them is not straightforward. It's a slightly difficult task to do. As of now, we do not have the tools to do it for like very complex tasks. And there are fewer standards compared to ML. For example, when you deploy machine learning, you have a lot of standards that you have to follow. But as of now, it has not been developed for neuromorphic computing yet. And let's go back. So that brings me back to the problem. What is our problem? Detecting the anomalies in edge devices with a lot of changing signals, right? So neuromorphic computing actually is it's very ideal for this use case. So one of the habituation is something in neuromorphic computing that it just reduces the response to repeated stimuli. For example, when you have the same signal over and over again, uh, your device does not need to respond to that signal, is what I'm saying. For example, I'm sure many of you would have not noticed that the AC is on right now or the fans are turning. You just tune that out of your head. That's same thing that's going on here. And I would actually like Samir to kind of elaborate on habituation a little bit.
Okay. Um, okay. Can I get a raise of hands? How many of you have heard of Pavlov's dog? Okay, one person. So, if you know this, you get this meme. Okay, so for all of you, I'll explain Pavlov's dog. Pavlov conducted an experiment where he started to ring a bell before he would feed his dog. Now, over time, the dog associated that ringing of the bell with the food, and eventually Pavlov came to the conclusion that he found that his dog was salivating before the food even came out just by ringing the bell. This is what habituation is. We what the brain starts to associate a stimulus with a response, and that stimulus here is the bell ringing, and the response would be the dog. And what we're trying to do with hands, is basically the opposite. We are trying to suppress the stimulus for the recurring recurring signals, and instead respond to the anomaly signals. The brain gradually reduces the stimulus when it keeps repeating, and that response fading is exactly the mechanism we are using in hands. So the practical benefits, this does not need that much label data or retraining. We'll show you the implementation that we've done just a minute. And it is local and interpretable. It does not require large global variables, as he said. And it is a rather simple mechanism to implement. Okay, next we'll move on to the implementation.
Okay, so here's what's going to happen. Okay, I will show you how we implemented. Yeah, just a minute. We'll just very quickly note on how we actually implemented it. Just but yeah, so it was written in C++, of course, to target efficiency and edge devices. We trained it on the ECG data. ECG 5000 is a very clean data set, which has around 5000 sequences of ECGs. Next one. Yeah, so we chose a global threshold. Each sequence, each of those 5000 sequences, we computed a threshold, which was the mean plus half of the standard deviation. This is pretty standard. And that continuous waveform, we made it a binary stream. The binary stream, I'll show you next. Yeah, so basically, true or false, right? If the stimulus is present, the response decays, which means stimulus is present means the same stimulus, the repeated stimulus. So the response decays, which means the neuron habituates. And if the stimulus is false, which means it's not there, then the response recovers. It shifts back to the baseline, is what I'm trying to say. And when you have your response greater than the threshold, then we flag a novelty event. So basically, each neuron has three parameters here: uh, a learning rate, which means how fast it habituates; a recovery rate, which means how fast it comes back to the baseline or regains sensitivity; and a novelty threshold. Next. So here we took three different neurons just to showcase three different timings. Uh, yeah, those are the parameters. You don't have to worry about that. Yeah. So before I show you the results, just a very quick note on complexity. So ECG is a time step of 140 seconds, which is not a lot, but enough to sense some sort of patterns going on here and there. So per time step, it is O of n because there are n number of neurons which do the computation. And the memory, since we're not storing anything, it should be O of 1 because it's constant. Okay. On the last note, we'll look at the results. So as you can see, this is the time step of 140. The blue is the ECG signal, and so what during normal response, which is the when the three neurons are above the ECG line, it's pretty normal, and the novelties are not flagged. Whereas when you see when novelties are flagged over there in the middle, even the response curves of the three neurons dip below the ECG line. Uh, yeah, so just a second. So I wanted to show you about the novelty over there. Each of the three neurons are showing you the novelty in the exact same place. That is only because have a global threshold as of now, and we've not trained them individually to have different thresholds. Uh, yeah. So this is individual response curve. As you can see, B is very slow to habituate. It detects the change very slow, and that's why it doesn't flag much novelty events compared to C. C detects change very fast, and that's why right from here it detects the change fast, and also uh, it's very sensitive because it's fast. And then you have A. Just a second. A is like in between B and C because the learning parameter was in between. Yeah. And we also compared, about the efficiency. We compared it to other novelty detectors like MAD, Z score, isolation forest, etc. And as you can see, a lot of times we agree on where the novelty is there, and a lot of times there is disagreement. That is mainly due to things like different thresholds or some sort of sliding window differences, all such things. But you can see the habituation actually occurring. In the left hand side, the first part, there are a lot of novelties flagged. And as you go on, the novelties flagged get lesser and lesser, which means it is habituating to the signal. And yeah, this is the main part, right? How much energy is this going to use on your edge device? Since neuron C was, go back, hey, don't show the meme just yet. Okay. Since neuron C was the fastest to find the novelty, it uses the most energy, which makes sense because every small shift it is calling a novelty. That is why it uses the most energy. And the completely opposite for B. B is very slow to detect the change and hence uses less energy. And A is in the middle as usual. Yeah. So that's pretty much it. And when we uploaded this to Canonical, we got some really nice insights into. Oh, hi, sir, you're right here. We got some very nice insights into what we can do next. Okay, just. Yeah, so a soft refractory gate, as what sir said, instead of lifting the thresholds after each time the neuron fires, can dampen the. We can add some sort of gain so that the response dampens. Is what I'm trying to say. And entropy as well. Right now we are not flagging. Right now we are not calculating entropy because I mean we should in the future. So it is susceptible to noise. So if we add some entropy, we can raise the threshold a little bit so that it doesn't go chasing some random noise in the signal. And later we can pull down that threshold. And this is something we thought of per neuron feature specialization. Right now, all three neurons look at the same raw data, but we are thinking uh, let one of the neurons look at something like an envelope or some sort of mean. So we'll see that in the future. Is okay. Yeah. And yeah, thank you. I would like to conclude here.